Okay. Today I talk about the paper that is called Neural 3D Scene Reconstruction with the Manhattan World Assumption. This is new paper. This paper solves the problem of reconstruction of 3D indoor scenes from multi-view images. And it is particularly interested in low textured planar regions reconstruction, which are common in indoor scenes and which are difficult to reconstruct usually. So they show in the paper that they use planar constraint that can be conveniently integrated into reconstruction method that are based on implicit neural representation. So they they used signed distance function or signed distance field as a scene geometry for representation of the scene, and use the Manhattan World Assumption for normals to regularize the geometry in floor and wall regions, and these floor and wall regions are predicted by two-dimensional semantic segmentation network. And they also introduce specific losses that perform joint optimization of semantic segmentation and geometry simultaneously. In this way, they can improve the original two-dimensional semantic segmentation and simultaneously improve geometry with planar constraint. Here's the method, the illustration. So they use implicit neural representation of 3D scene. They use differential volume rendering to build pixels with pixel color, and also semantic logits here. And okay, so this is the illustration here. The network, the outputs of the network, and renderings here, and different losses to produce to improve both segmentation and 3D scene geometry. Here, and this is the network architecture they used here. For this, the network takes as inputs spatial point, view direction, and outputs signed distance field or function, color, and semantic logits here. So some implementation details: they use PyTorch and they use DeepLab version 3 plus for initial two-dimensional semantic segmentation. They trained the network on one NVIDIA card, and for one scene it takes 5 hours for the training. The images are size 640 by 480 here. They work with two datasets. ScanNet is an RGBD video dataset, and 7 scenes, which are RGBD frames taken by handheld Kinect RGBD camera. Here. So about losses. The first one is the training with only images, and they use photometric losses for this. This is a case here. Then they add depth maps and for training from RGBD camera. This is B case. Then additionally, they introduce a loss function for normals, for floor points and wall points, and this segmentation initially are taken from two-dimensional segmentation. And finally, the final case is the joint optimization when they refine both the semantic labels and 3D scene. Here are some table with numbers. They used solution that is called volume SDF from another paper. This solution combines volume rendering techniques and implicit differential renderer to learn and reproduce 3D shapes from 2D images. And they added these different losses sequentially to see the improvement they give. And here also the results of reconstruction for these improvements on ScanNet dataset. And this is the comparison with other methods like CallMap and CallMap with planar constraints. There is some such kind of version of CallMap here, and they say that their method performs much better than any other method. This is table for this comparison for different metrics. And here they illustrate the semantic, the improvement of semantic segmentation with their losses. So they perform additional semantic segmentation in 3D space, not just as the initial network gives two-dimensional segmentation, but they combine three-dimensional geometry with semantic segmentation to improve. And they also say that their model allows to generate a new view, synthesize new view of 3D scene that are different from the views that we used for training here. So as a conclusion, the authors, the key idea is to utilize semantic segmentation in planar regions to guide geometry reconstruction. And they use 3D semantic segmentation to improve this segmentation and use it jointly to optimize 3D reconstruction with Manhattan assumption. And the experiments showed that the proposed method really works really good in planar regions with poor textures. So there is a limitation. They say that they use Manhattan world assumption, but the method can be generalized for other kinds of geometry. But for now, it is limited to this. They have the project page, and they have a GitHub also code for the implementation. A short video here, and here's some demonstration of what their method can do. So this is how their reconstruction looks actually. So for different scenes here. Well, that's all.